Okay, so welcome back. We're going to look at the second part of section 6.1, and I'm going to show you how to take what we've learned in section 6.1, part 1, and apply it to developing confidence intervals, in this case for a single proportion. So let me just remind you that from our work in chapter 5, we saw that when the underlying sample statistic is approximately normally distributed, then a 1 minus alpha confidence interval for the parameter is given by best estimate plus or minus a z cutoff that's tuned to the confidence level that we're after, and multiplied by the standard error. So this is a fairly general formula. We can apply this in many situations. Now, what can we do? Based on what we've learned already in section 6.1, we can now use a formula, a theoretical formula, to compute the standard error, and we don't have to rely on simulation to get the value. So we can, in some sense, relieve ourselves of having to go and create a dot plot just to calculate the SE. So this will be another layer removed from simulation. We'll be able to do these problems without simulation. All right. Let's take a look at what this confidence interval formula looks like in the specific case of a confidence interval for a single proportion. So we have to imagine that we have a population that has an attribute A with proportion P. And once again, that attribute could be almost anything, some aspect of the population that you're insanely interested in. So you have some attribute, and within the population that has a proportion P, our goal is to try to estimate where is P. Develop a confidence interval for the location of that parameter. So our goal is to develop a 1 minus alpha confidence interval for P. So let a random sample of size n be drawn from the population, and let P hat be the sample statistic, our best estimate of P. So that's going to be the proportion within the sample, the proportion of our attribute within the sample itself. That's going to be our best estimate for P, but we're going to have to put some slop onto it in order to develop our confidence interval. So here's what we do. We compute n times P hat, and we say if that's bigger than or equal to 10, and if n times 1 minus P hat is greater than or equal to 10, so this is our validity check for normality, then the 1 minus alpha confidence interval for the population proportion P is going to be, well, as we said in the previous slide, best estimate plus or minus z cutoff times SE, but now we can replace SE in this specific case by this formula. All right, so the confidence interval is now going to take the form P hat plus or minus z cutoff times the square root of P hat times 1 minus P hat over n. So all we're doing is we're substituting in best estimate as P hat, and SE is given by this formula. All right, now, there is a bit of a cheat here. We're not going to stress out about this, but if you really think about this, this is not exactly the formula for SE that we developed earlier. That formula should be P times 1 minus P divided by N. So strictly speaking, this is not quite right. On the other hand, P hat and P will be close to each other, and this is not going to make that much of a difference. There would be no way for us to use P in place of P hat here, because we don't know what P is. And so in some sense, this is all we can do. And it turns out to be not that big of a deal. All right, so there is this little bit of a fudge here, but we're not going to worry about it. All right, so we've got this formula for our confidence interval that we can now use just based on the value of P hat and on the specific confidence level that we need to work at. All right. I want us to work through a problem here, and in this problem I want to show you kind of the development of our procedures for working through confidence intervals. We're going to do this same problem in 3 different ways according to how we've learned how to develop these confidence intervals. So we're going to kind of work it up in succession here. So a random sample of size n equals 150. All right, so we'll cut here. All right, so our next task here, I want to finish this this part 2 of section 6.1, working on a couple of problems. Now, this first problem, what I want us to do is I want us to work the same problem in 3 different ways. And this is going to follow kind of the 3 different developmental phases that we've been discussing. So we'll get to that in just a second. But the problem is this. A random sample of size n equals 150 Reese's Pieces, and I have to say I've been a little remiss in this. It is supposed to have this apostrophe here. It's possessive, so I apologize to Reese's Pieces for my previous work here. I've been sometimes neglectful of that apostrophe. So 150 Reese's Pieces contains 72 orange-colored pieces. That gives us a p-hat of 0.48. We want to develop a 90% confidence interval for the population proportion of orange-colored pieces in Reese's Pieces. And we want to do this in 3 different ways. Method 1 is something that we learned in section 3.4. We're going to use stat key to create a bootstrap dot plot and count the dots, carve out the middle 90%, and give us the confidence interval. All right, that's method 1. Method 2 is commensurate with what we did in chapter 5, section 2. We're going to use stat key to create a bootstrap dot plot, but then we're going to take the SE from the dot plot and develop the confidence interval using our formula that we learned in section 5.2. Now we're going to do that problem on the whiteboard. All right, then we're going to close this problem by doing the same problem now. We're going to use the formulas for the confidence interval developed in this section. And this is going to give us a way to compare our answers as generated by these 3 different kind of very distinct methods. And hopefully we'll see that they're all giving us reasonably close answers. All right, let's take a look at problem 1. We can do this one here still at the computer. All right, so let's just remember we've got 72 orange-colored pieces out of a sample of size 150. So let me start over just so you can kind of work this with me. So let's say you've got stat key loaded up. We're going to do a bootstrap confidence interval for a single proportion. So follow along with me. We're going to edit the data, and we're going to say we had 72 with attribute A, in this case orange-colored pieces, out of a sample of size 150. That's going to give us a proportion you can see over here of 0.48. Now we want to imagine what would happen if we did this kind of sampling over and over again. So let's generate several thousand simulations of sampling from these Reese's Pieces. Okay, and here's the dot plot that's emerging, and all we have to do is hit to tail. It defaults to a 95% confidence interval, but we can easily edit this and ask it to give us a 90% confidence interval. And let's write this down. So for comparison purposes, our confidence interval is going from 0.413 to 0.547. Okay, so we'll write those numbers down, and we'll come back with the whiteboard, and we'll work those next problems. Let's just review. We'll come back to the whiteboard, and we'll review this problem viewed through just grabbing the SE from the bootstrap dot plot, and we'll use the formulas that we've developed in this section. Now, before we leave, since we're going to need this for problem 2, let's go ahead and make note that the standard error for this dot plot, we'll need that. I'll write this down. The standard error for this dot plot is 0.041. In the center of our dot plot, the mean of our dot plot, we'll use 0.48. The dot plot is off just by this in the thousandth place, but we'll use the 0.48 as the mean of our dot plot. So when we come back with the whiteboard demonstration of problem number 2, we'll be using a normal distribution centered at 0.48 and an SE of 0.041. So I'll join you at the whiteboard, and we'll finish up problems 2 and 3, or parts 2 and 3 of this problem. Okay. All right, so now we're going to try to do the same problem again using stat key just to give us the SE from the dot plot. But the rest of it we'll develop using the theory. And so this will be as we did in section 5.2. So let's just remember what we know about our problem already. We know that our best estimate is p hat equaling 0.48. That's going to come from the 72 orange candies out of the 150 total. That's a p hat of 0.48. Now, from the dot plot, we got that the standard error was 0.041. And so our 90% confidence interval is going to have the center at 0.48, and it's going to be plus or minus the z cutoff that's appropriate for a 90% confidence interval. So if we think this through, that's leaving 10% out. That's going to put 5% in the left and the right tail, so we should use a z of 0.05 for our cutoff value. And then we're going to take the SE and tuck that in here. Now we probably remember that z of 0.05 is 1.645, and our standard error is 0.041. And so the margin of error, which is the product of these two, let's calculate that first. 1.645 times 0.041. That margin of error is on the order of 0.067. I'm just going to store that in my calculator. And now I want to do 0.48 plus the margin of error and 0.48 minus the margin of error to get my two endpoints for my confidence interval. So 0.48 minus the margin of error is going to be about 0.412 or 0.413, and 0.48 plus the margin of error will be about 0.548. And that agrees pretty well with what we got earlier from just using the dot plot alone. All right, so that fulfills method 2. And now our last part of the problem now is to do this using method 3, which is using theory only. So we're not going to get the standard error from the dot plot. We're going to have to develop that from the formula. So let's see how that would look. The rest of the calculation is going to look very much the same. We just have to notice that the standard error, if we're calculating it from the formula, is what I get by using the p hat and 1 minus p hat, or its complement, divided by the total number of, or the total sample size. And so that's going to give us and don't forget to take the square root, because that's a very common mistake. Take the square root, and we're going to get, and after you round, it's going to be 0.041. Now that's exactly the same standard error that we got when we used the dot plot. So the rest of this is going to look the same, right? Our 90% interval is going to be the center plus the z cutoff. It's the same z cutoff that we had before for 90%. That's going to be the z 0.05. That's the 1.645. And the standard error is going to be 0.041. And that's going to give us exactly the same interval that we saw before. So you can see whether we do it by method 1, where we rely entirely upon the dot plot, whether we do it by method 2, where we have this mixed strategy of simulation and theory, or whether we do it by problem 3 or part 3, where we use theory only. We're getting roughly the same confidence interval in all 3 cases. Now, I do want you to be able to do it by all 3 methods, so practice each of these methods and make sure you know how to do all of them. Okay, great. Let's move on to the next problem.
Okay, our last problem, and again, we'll work this one at the whiteboard, but let's read this together. In a survey of 2,255 randomly selected U.S. adults aged 18 or older, 1,787 of them use the internet regularly. Of the internet users, 1,054 use a social networking site.
Find and interpret a 95% confidence interval for each of the following proportions. First, the proportion of U.S. adults who use the internet regularly. Second, the proportion of U.S. adult internet users who use a social networking site. And finally, the proportion of all U.S. adults who use a social networking site. Now, with this last one, we want to answer or look at this claim. Use the confidence interval to estimate whether it is plausible that 50% of all U.S. adults use a social networking site. So we'll come back to that follow-up question once we have this confidence interval in part 3 developed. So let's go to the whiteboard. We'll develop each of these 3 confidence intervals. In this case, we will use only the methods of section 6.1. So we're going to use the formulas that we've developed within this section to handle these problems. So let's go to the whiteboard and see how each of these comes out.
All right, so the last problem we're going to work from this section on confidence intervals is this problem 6.24. I've put this Venn diagram over here to the side to kind of remind us about how all these numbers are connected to each other. So if you remember, the sample was 2,255 U.S. adults. 1,787 of them use the internet regularly. And then within that group, there were 1,054 who used social networking. So that just helps us kind of keep track of the numbers, because as we work our way through this problem from problem 1 to 2 to 3, we're going to be looking at different proportions within this. Okay, so the very first problem is to find a confidence interval at the 95% level for the proportion of U.S. adults who use the internet regularly. So we're going to be looking at this proportion and building a confidence interval for the internet regular users. Okay, so our best estimate, let me just use BE for that. That's going to be this proportion, the 1,787 out of the 2,255. And that's going to give us the proportion of the adults that use the internet regularly. This is our best estimate for it, at least. So 1,787 divided by 2,255, and we'll call that 0.792. Okay. Now, before we develop our confidence interval, we should stop and calculate the standard error. Now, we're doing this completely by theory, so this is completely in terms of the methods that we've developed in this section. So we will take the 0.792. I have to find its complement. That's going to be 0.208. And I have to divide by the total sample size. That's the 2,255. I'll remember to take the square root at the end, so let's see what we get. 0.792. 0.792 times 0.208 divided by 2,255. Take the square root. I'm getting a number on the order of 0.0085. Okay, so that's going to be our standard error for this problem. Now the rest of this goes down pretty easy. Our 95% confidence interval, so at the 95% level, our confidence interval is going to be our best estimate plus or minus what we get by using our z cutoff. Now we're working at the 95% level, so we're going to use a z of 0.025, and that's the familiar 1.96. And then we just have to bring our SE into the problem. The margin of error is going to be 0.0085 times 1.96. That's on the order of 0.0166, so I'm going to store that. 0.792 plus, recall 1. So my right endpoint is going to be 0.809 roughly. And my other endpoint is going to be 0.792 minus, and that's going to be 0.775. Okay, so we're 95% confident that the true proportion of internet users amongst the U.S. adults is covered by this interval from 0.775 to 0.809. Okay, so that's the solution to problem 1. Problem 2 asks us to basically repeat the same calculation but for a different proportion. This is the proportion of U.S. adult internet users who use a social networking site. So there we're going to look at the ratio between these two numbers and try to estimate the proportion. All right, so all we have to do is go in here and change out some of our work. So in this case, we're now going to look at the ratio of the 1054. Those are the ones that use social networking, and divide that by the total number that use the internet at all. Okay, so that's going to be 1054 divided by 1787. That's giving me a sample proportion of 0.5898. Let's just call that 0.59. Okay, 0.590 after rounding. Okay, our standard error that goes along with this is going to be the 0.59, and then its complement, which is going to be what? 0.41 divided by the sample size of 1787. So that's going to be our formula for the standard error. And when we do this calculation and work this out, we're going to get 0.59 times 0.41 divided by 1787. Take the square root. We're getting a standard error on the order of 0.0116. Okay? Now, all we have to do to get our 95% confidence interval is put all this together. We're going to take our center, and we're going to add and subtract the z cutoff, which is still that 1.96, times our standard error, which is 0.0116. I'll first calculate the margin of error here. Our margin of error is on the order of 0.02. I'm going to store that. All right, here we go. Let's get our two endpoints. 0.59 minus the margin of error puts me at about 0.57. And then 0.59 plus the margin of error puts me at about 0.61. All right, so we're 95% confident. We're 95% confident that the true proportion of social network users amongst the internet frequent users is covered by this interval. So that's the way we would kind of articulate this conclusion. All right, we have one less problem, or one less part to this problem. The first part of the problem is to develop a confidence interval for the proportion of all U.S. adults who use a social networking site. Now this is slightly different than the problem we just worked, because now we want to look at the ratio between these two numbers. All right, now we're looking at the 1,054 amongst the 2,255 that were sampled. Okay, so this is going to change accordingly. And this would be a good time for you to pause this and try to work this out for yourself and see if you get the same answer that I get. So if you want to do that, just pause this video at this point and try to work it out. We're going to be working with the p-hat that we get by taking this ratio in this case. So, all right, here's my development of this. We've got the 1,054 people who use social networking regularly out of a sample of 2,255 U.S. adults. That p-hat is going to be 1,054 divided by 2,255. That's, let's call it 0.47. Okay, so about 47% in the sample. The SE that goes along with that, according to our theory, is going to be the 0.47 times the complementary 0.53 divided by the sample size, 2,255. So that's going to give us an SE that's on the order of, let's see, 0.47 times 0.53 divided by 2255. Take the square root. That's on the order of 0.0105. Let's call it 0.011. That's close enough. Okay, so our 95% confidence interval. It's going to be the usual thing. We're going to take our center. Our best estimate forms the center of our interval, plus or minus the Z cutoff that's appropriate for the 95% confidence level, and our standard error. All right, so we've seen this kind of calculation many times. Our margin of error is on the order of 0.202156, so we're just going to store that. Let's get the endpoints of our interval. So we have 0.47 minus, that's going to go from 0.448 and this is going to be 0.492. Okay, so there's our 95% confidence interval. We are 95% confident, right? We are 95% confident that the true proportion of people that use social networking amongst the U.S. adults is captured by this interval, or is contained by this interval, or is covered by this interval. Now, the very last part of this part 3 was to use the confidence interval to estimate whether it is plausible that 50% of all U.S. adults use a social networking site. And we would have to conclude that the answer is no. Notice that this interval, this 95% confidence interval, does not contain 50%. So it is actually, we have 95% confidence that this true proportion is actually less than 50%. So we would answer this last part with a no. We are fairly certain at the 95% confidence level that the true proportion is in fact whatever it is. Let's just call it P. Whatever this true proportion is, based on this calculation, we're fairly confident that that is less than 0.5. Okay, so that's the end of problem 6.24, and that's the end of this section. So I'll catch you on the other side. Bye-bye.